There's a small but growing literature on a phenomenon that has no name to speak of. I call the phenomenon the indeterminacy of computation, because every good phenomenon should have a name. Although many of those who write about the phenomenon seem to think that it's a bad phenomenon. Indeterminacy is a problem, they say, and a solution is required, a solution for which the hunt is on. But I don't see things that way at all. Indeterminacy is simply a feature of computation. It's an important feature and a useful feature. So far from attempting to purge computation of indeterminacy, we should embrace it, or so I shall be suggesting. But first I want to mention my collaborators and friends. I've greatly enjoyed my adventures with these various people, exploring the largely uncharted terrain of computational indeterminacy. Firstly, Oroning Shagrir, my long-term collaborator on various fascinating projects. That's the amazing city of Jerusalem spread out behind Oroning. This talk is in fact the long version of my half of a short talk that Oroning and I gave together a few months ago, and he'll be talking about indeterminacy as well later in this conference on Saturday. Next, Marty Wolf. When Marty sent me this photo, I thought he must have been exploring in the Amazon basin or somewhere, but it turned out it's just Rhode Island in New England. Near Fresco. Looking very happy in his lecture theatre. Near and Marty and I have just published a paper titled simply The Indeterminacy of Computation. I'll be mentioning this paper again later in the talk. The shape of the talk. First, I'll be describing a piece of work by Ralph Slutz, which he did around 1950. As far as is known, Slutz was the first pioneer of computational indeterminacy. Then I'll take a look at what happened to this idea after Slutz. Around 2000, Shagrir took indeterminacy to a whole new level. I'm going to explain what Oroning did. Then we come to the heart of the talk, waveforms and pulses. I guess you may not think that pulses sound a very promising topic for a talk by a philosopher, but I can assure you that pulses are not only fascinating, I think they're also philosophically important. As I'll be explaining, Alan Turing was very keen on pulses, and pulses were the basis of Slutz's discovery of computational indeterminacy. In section 5, I'm going to distinguish between 3 different computational levels that are important in relation to indeterminacy. One of these is the pulse level, or the P level. On my analysis, all the most important action, indeterminacy-wise, happens at this level, the pulse level. In section 6, I'm going to introduce 2 key concepts for understanding computational indeterminacy, the concepts of pulse parsing and pulse reparsing, as I call them. Armed with these concepts, it's possible to give an illuminating and unifying account of the discoveries made by Slutz and Shagrir. The next section turns to implementation. If pulse parsing and reparsing are to be useful practically, it must be possible to mechanize them. Then, objections. Objections to any or all of the above. After all, this is a philosophy talk, so there does need to be some argy-bargy. So that's largely where we'll get it in section 8. Although there may be some little bits of argy-bargy elsewhere in the talk too, I must confess. And finally, potential applications. What uses could indeterminacy have? And perhaps it may not only be useful to engineers. In the paper I mentioned just now, Near and Marty and I speculate that evolution may have made use of computational indeterminacy, as I shall explain at the end of the talk. But first, Slutz. I initially encountered a description of the indeterminacy of computation in 1995, although at that time, of course, the phenomenon had no name. This was when I was doing research into the history of computing, and I found a tape-recorded interview in the archives of the Science Museum in London. The interview was with one of the original pioneers of electronic computing, and it was recorded in 1976, but it described events that happened long before that, in the late 1940s. The interviewee was Ralph Slutz, of course. Here he is, from a long time ago. This may have been the 1930s or 1940s, I think. He looks very, very fit. I like to think of Slutz as the discoverer of the indeterminacy of computation. Slutz studied electronics at MIT. He was basically an electronic engineer for the whole of his life. And after the war, he worked with the great computer pioneer John von Neumann at Princeton University. Then, in 1948, Slutz shifted to the US Bureau of Standards in Washington, D.C. And there he was prime mover behind what they called the SEAC computer, the Bureau of Standards Eastern Automatic Computer. That's what they called it. The SEAC was one of those glorious, gigantic first-generation computers, based on vacuum tubes, of course. All the vacuum tubes and the many, many racks of electronic circuits are hidden away behind that tidy row of doors that you can see at the back of the photograph. If you open the doors, you would see this great untidy tangle of electronics. In the foreground, you can see some of the peripheral devices. And over on the right-hand side, there's what they called the control desk, with one of the operators sitting at it. The SEAC first ran a program in DC, where it was built, in 1950. And that makes it the very first modern computer to run in the US. That's to say, it was the earliest universal Turing machine in electronic hardware to run a program in the United States. Although, of course, the Brits had got there first, 2 years earlier, with their Manchester computer, with which Alan Turing was himself involved. While Slutz designed the SEAC circuitry, he realized that his machine was going to need many more AND gates than OR gates. It was just a feature of its design, given what they wanted to use it for. But constructing an AND gate required more electronic diodes than were needed for an OR gate. So it occurred to Slutz that if only the ratio of gates could be reversed so that OR gates predominated in the computer, he could achieve a significant reduction in the number of diodes required, and thus a reduction also in the cost of building and running the computer. In the interview, he described his new insight. He said, "In playing with Boolean algebra, I realized that if we just took our logical design and replaced all AND gates by OR gates, and all OR gates by AND gates, and let the absence of a pulse represent a 1 instead of the presence of a pulse representing a 1, we could achieve this reduction." Slutz built a working prototype involving this principle, but because of the difficulty people had understanding his idea, he eventually abandoned it and simply settled for more diodes. It's kind of a sad story. He said, "I remember the difficulty I had explaining to everybody that when they saw a pulse, it meant 0, and when they saw a no pulse, it meant 1. Let's look in detail at Slutz's clever idea. To represent things diagrammatically for clarity, what Slutz was talking about were gates, logic gates, with 2 input channels. What goes into a gate and what comes out? As Slutz mentioned, pulses go in and pulses come out. So the coloured curves here represent voltages varying between high and low. Here the pulses are the peaks and the troughs are the no pulses. According to the usual convention, a pulse signifies 1 and a no pulse signifies 0. Slutz says let's reverse the normal convention and let a no pulse represent 1 and a pulse represent 0. That way he can turn OR gates into AND gates and make a big saving on equipment. Here's how his idea works. Consider a particular gate S for Slutz. So, letting P stand for pulse and N stand for no pulse, gate S behaves as shown in the following table. So in the first row of the table, it says that if both inputs are pulse, then the output is a pulse. And the second row says that a pulse and a no pulse as inputs produce a pulse as output, and so on. The table simply summarizes the way gate S is wired up. That's how it's been engineered to behave in that way. Now, if a pulse signifies 1 or true, and a no pulse signifies 0 or false, then S is computing inclusive disjunction, since table 1 becomes the following truth table. And that's the very familiar truth table for inclusive disjunction, or I-OR. The output is always true, except in the case where both inputs are false. Now for Slutz's switcheroo. If a pulse signifies 0 and a no pulse signifies 1, then S is computing conjunction. You get kind of the reversal of the first table. And that's the very familiar truth table for conjunction. The output is always false, except in the case where both inputs are true. So Slutz's switcheroo turns the gate into an AND gate. For want of a better technical term, I call Slutz's switcheroo slutzing, with a lowercase s. So in slutzing, you systematically exchange the 1s for 0s and the 0s for 1s. It seems both trivial and yet mystifying, doesn't it? Is gate S computing conjunction, or is it computing disjunction? Well, if nothing more than the pulsed behaviour of the gate is considered, as depicted in the table at the top of the slide there, it's simply indeterminate whether the gate is computing disjunction or conjunction. So that's the indeterminacy of computation, as the idea first manifested in Slutz's work. Adding a footnote to what Slutz achieved, there's space for a new concept here. I call it multiple specifiability. The concept of multiple realizability is well known. Architectures, algorithms, and computations are multiply realizable. Two or more different computers, one made of vacuum tubes, say, and another that is solid state, can carry out the same computation. It's a very familiar idea. The concept of multiple specifiability is a relative of multiple realizability, almost an inverse. A multiply specifiable device or structure is one that, like the Slutz gate S, indeterminately carries out two or more computations. Gate S is multiply specifiable because it has two specifications. It's an AND gate and it's an OR gate. So that's multiple specifiability. So what became of Slutz's wonderful idea? Well, unfortunately, Slutz never published. He was an engineer. He built machines, and publishing just wasn't his thing, least of all publishing on the philosophy of computing. But it was clear from the way he spoke in the tape-recorded interview I found that he was well aware of the idea's importance. So Slutz rode off into the sunset, and not much happened for the next 40 years. So, how did the idea re-emerge? Roy Sorensen visited me in New Zealand in 1996. This is Roy in the Southern Alps. And that's me, reflected in Roy's mirror lenses as I took the photo, on a dangerously steep snow slope, as I remember. It's actually a highly appropriate photo, since in New Zealand, Roy was working on his wonderful article about mirror computation. Here it is, mirror notation, published in 1999. Roy wasn't considering the indeterminacy of computation at all. His article was about something entirely different, which he called perspectival computation. As Roy says in the abstract, in perspectival computation, the problem solver obtains the output by merely altering his or her orientation toward the input. The computation happens simply by the problem solver moving relative to the input. So this is quite different from the indeterminacy of computation. But Roy was interested in Boolean dual functions, which, you can see why. They kind of, a dual mirrors the function of which it is a dual. And I was bursting with enthusiasm for Slutz's discovery. So I told Roy about Slutz, and I wrote a draft paragraph for his paper, which he included after a bit of editing. So this is Roy's paragraph after the editing. He said, "Interest in the economies offered by duals emerged early in the history of computing. Ralph Slutz, one of the pioneers of American computing, knew that OR gates required fewer diodes, or equivalently vacuum tubes, than AND gates. Inspired by a study of Boolean algebras, Slutz tried to simplify the design of the standard electronic automatic computer." I've just noticed that Roy's missed an S off there in the title. SEAC began running in 1950 and was the first American electronic stored program machine. Slutz proposed that every AND gate be replaced by an OR gate and vice versa, and then he reinterpreted pulse as false and no pulse as true. Although Slutz calculated that this achieved a 30% saving, he had trouble explaining his dual machine to potential users and operators. Consequently, his clever design was not implemented for SEAC. So that was Slutz's entry into the philosophical literature, together with his, at that time of course still nameless, discovery. The next appearance of the idea was in a book chapter by Ned Block. In 1995, he published an absolutely tantalizing sentence in his chapter of this 1990s classic, An Invitation to Cognitive Science. The sentence appeared only in the second edition of the book, not the first. The first edition was 1990, I think. And the tantalizing sentence appeared in the second edition. Let's have a look at what Block wrote. He said, "The states might be a 4-volt and a 7-volt potential. If the two input states of a gate are the same, say 4 volts, and the output is the same as well, 4 volts, and if every other combination of inputs yields the 7-volt output, then the gate is an AND gate, and the 4-volt state realizes 1. Alternatively, if the 4-volt state is taken to realize 0, the gate is an inclusive OR, either or both gate." So there it is. That's the Slutz switcheroo right there. Block doesn't explain this remark, and he doesn't so much as mention it again in his chapter. And as I said, it isn't even there in the first edition, though the surrounding sentences are pretty much unchanged. Block just stuck it in parentheses, but made nothing of it. So I was curious. I wrote to him to discover the story behind this remark, and he sent me some slides, and he said, "All the ideas in the slides were ones I developed in the 1980s on thinking about the intrinsic observer-relative distinction." I think the intrinsic observer-relative distinction probably became big news as a result of Searle writing about it in Behavioral and Brain Sciences, and various other people discussing it quite intensively back in the day. So Bloch continued, I was giving some talks on this in the late 1980s, and I used that material in my Minds and Machines courses then and for years after that. Here's the key slide from the bunch of slides that Bloch very kindly sent me. It's a very elegant diagrammatic exposition of the Slutz switcheroo. But Bloch didn't know anything about Slutz. He reinvented the switcheroo for his own purposes, relating to observer relative versus intrinsic. I'll return to this interesting remark of Bloch's at the bottom right later on in the talk. He says, but it's an intrinsic fact that something is an and or, but not a XOR gate. So it's and inclusive or, but not an exclusive or gate. So as I say, I'll come back to that later. But first, on with the history of the idea. And here Oroning enters the story around 2000. I don't think Oroning knew anything about Slutz at that time either. But what he did was introduce something even more intriguing than Slutz had. And he published his ideas in his now famous article in Mind in 2001, Content, Computation and Externalism. So, as I've said, Slutz described the procedure that I'm calling slutzing. Oroning introduced the procedure that I will call Oroning. So, section 3. By means of a well-chosen example, Oroning brought in a marvelous new twist. He wrote about a system that he called P. So P is a system consisting of an AND gate and a XOR gate, an exclusive OR gate. So Oroning said, let us first consider the general case. Take the physical system P. Suppose it turns out that flip detectors of P are actually tri-stable. Imagine, for example, that the AND gate in P emits 5 to 10 volts if it receives voltages higher than 5 from each of the two input channels, 0 to 2.5 volts if it receives under 2.5 volts from each input channel, and 2.5 to 5 volts otherwise. Let us also assume that the XOR gate emits 5 to 10 volts if it receives over 5 volts in one input channel and under 5 in the other, 0 to 2.5 volts if it receives under 2.5 volts from each of the input channels, and 2.5 to 5 volts otherwise. Let us now assign the symbol 0 to emission reception of under 2.5 volts and 1 to emission reception of 2.5 to 10 volts. Under this assignment, both the AND gate and the XOR gate are seen as OR gates. So that's Oroning. Let's look at Oroning more closely. So there is a gate. Call it O, the Shagrir gate. Like the Slutz gate S, the Shagrir gate has got 2 inputs and 1 output. But unlike the Slutz gate, O is what Oroning calls a tri-stable gate. He means by tri-stable that O operates with 3 voltage ranges. So they're 5 to 10 volts, 2.5 to 5 volts, 0 to 2.5 volts. If the top and the middle range are grouped together and labelled 1, then the gate O computes 1 Boolean function. But if the middle and lower range are grouped together and labelled 0, then O computes a different Boolean function. That's Oroning. What is switched is the allegiance of that middle state. So what exactly is going on here? And is Oroning the same as slutzing or different? On this same or different question, I should explain that different subsets of Oron and Near and Marty and Jack have different views. I'm going to give you my take on same or different. It's one of the key questions in the area. But first, before tackling the same or different question, I want to present my analysis of Oroning and slutzing. And to do that, I need to talk about waveforms and pulses. So here is a nice regular waveform. Amplitude on the vertical axis, time on the horizontal axis. The highs and lows may be fluctuating voltage, for example, or they may be highs and lows in fluctuating water pressure. There was a famous computer called Maniac, which worked on the basis of fluctuations in water pressure. It was designed by a New Zealand economist, and so far as I know, only one was ever built, unsurprisingly perhaps. Or again, the highs and lows may be light intensities. Back in the 1990s, Roy Sorensen and I came up with a description of a computer consisting of nothing but mirrors and light. So waveforms are multiply realizable, in other words. But for present purposes, let's think of them as fluctuating voltages. Waveforms come in many different shapes. To get a square wave like this, you have to shape the wave by means of electrical circuits designed to do exactly that. The shape of this sawtooth wave has been carefully crafted by electronic circuitry for purposes known only to the designer of the circuitry, namely Alan Turing. It's from one of the figures in Turing's design for his automatic computing engine, or ACE, another of the first generation of electronic computers. In this case, the irregularities are due not to design, but to distortion and attenuation. Waves can get kind of beaten up as they travel about a computer. In Turing's case, this happened especially as the waves travelled through the long columns of mercury that he used as the ACE's high-speed memory, the so-called delay line memory. Once a waveform got as beaten up as that, Turing would push it through a circuit to clean it up and restore its crisp shape. The durations of the wave crests matter. What you're looking at here is a no pulse, followed by a pulse, followed by a no pulse, followed by two pulses. There are the pulses and the no pulses clearly marked. Conventionally, the pulses would signify 1 and the no pulses 0. Or you can do the Slutz switcheroo. I'll briefly mention waveform equations. A waveform equation summarizes the physics of a wave. So a waveform equation describes the shape of the wave as a function of time. Disregarding complicating factors like attenuation and distortion, the waveform equation for a very simple wave could be a straightforward trigonometrical equation along the lines of... So that's telling us that the amplitude of the wave at time t, the height of the wave above the horizontal axis, is a result of multiplying the maximum amplitude, which is a constant, the highest it ever gets, by the sine of the wave's angular frequency times t. But things are not so straightforward in the case of wilder waveforms, such as these two that we've already looked at. The waveform equation may be much more complicated in the case of shaped waves like the one on the left, or where there is attenuation or distortion, as with the one on the right. Gates have waveform equations too, summarizing the physical behavior of the gate. Here's a schematic representation of a waveform equation for a gate. what it's saying is that the waveform at the output is a function of the waveforms at the inputs. Now let's have a look at what Alan Turing had to say about pulses. Those who built electronic computers in those early days were often called pulse engineers, and Turing's post-war writing brought out the importance of pulses. He presented his automatic computing engine as a pulse processor in his design report in 1945 and in some lectures that he and his assistant Wilkinson gave in 1946 to 1947. Two of the most significant documents in the history of computing, in my view. Turing explained that trains of pulses circulate through the machine. The pulses are stored, transmitted, delayed, suppressed, and reproduced. Pulses are transformed into no pulses, and no pulses into pulses. Trains of pulses are divided into smaller groups, which Turing called words. Threshold circuits carry out such jobs as, he said, to ascertain if two pulses coexist in two channels simultaneously. Pulses are counted and pulses are added, and so on. You could put it this way: pulses are the effectors of digital computation. On one level, digital computation simply is the processing of pulses. I want to describe three separate computational levels: the W, P, and B levels. There are more levels than these three. For example, there's Mars algorithmic level, there is the so-called ecological level, there are various semantical levels, there are Newell's instruction level and system level and knowledge level. But I think that these three, W, P, and B, are the most important in connection with the indeterminacy phenomenon, especially the pulse level, or P level. So starting at the lowest level, level 1, that's the waveform or W level. Level 2 is the pulse or P level, where certain regions of the wave are designated as pulses and other regions are designated as no pulses, as in the example that we've seen. And level 3, the highest level, is the Boolean or bit or B level. This results when the pulses and no pulses are labelled with 1 and 0. So as we've seen, to Slutz is to do a B-level switcheroo. You just change the labels at the B level. But what exactly is Oroning? Here's my analysis. Let me tell you about what I call pulse parsing and pulse reparsing. Take a waveform. Next, select a threshold. What is above threshold is a pulse, and what is below threshold is a no pulse. So that's pulse parsing. You decide which parts of the waveform are the pulses by stipulating a threshold. And a piece of the curve, piece of the wave, counts as a pulse if and only if it's above the selected threshold. Here's another example. This time we start with a more irregular waveform. So there are 3 wave crests of very different heights. A threshold of 2.5 volts is selected. So this leaves crest A and crest C above threshold and crest B below threshold. So there are 3 crests but only 2 pulses. Here are the pulses shown more clearly. Thresholding at 2.5 volts produces the pulse train pulse, no pulse, pulse. Next, an example of pulse reparsing. We start with the same waveform. This time we select a higher threshold than before. Now both crest B and crest C are below threshold. So on this reparsing of the waveform, there is only one pulse. There it is, with its two no-pulse neighbours. By thresholding at a different level, reparsing occurs, and the same waveform constitutes a different train of pulses. For ease of reference, I'm going to use Z for the voltages in the region below the 2.5 volt threshold. And I'm going to use Y for voltages in the region between the two thresholds. And I'll use X for voltages in the region between the 5 volt threshold and, say, 10 volts, just to choose a level that's well above the height of any of these wave crests. Now, let's look at the effect of that pulse reparsing has on a gate. Call the 5 volt threshold pars the high pars, and the 2.5 volt pars the low pars. And consider a gate G with the following W level behavior, the following waveform level behavior. It's rather a complicated table, but to take it a row at a time, the first row is saying that if both inputs are in the range 5 to 10 volts, then the output is in the range 5 to 10 volts as well. And the second row says that if input 1 is in the range 5 to 10, and input 2 is in the range 2.5 to 5, then the output is in the range 2.5 to 5, and so on and so on. Gate G has been designed to display the behavior in this table, and the table simply summarizes G's designed behavior at the waveform level. On the high pars, only X is pulse, and Y and Z are no pulses. So on the high pars, G's P-level behavior, pulse level behavior, is described by the following table. In the high pass case, X gets replaced by P's, and both Y's and Z's get replaced by N's. Some of the lines in the table are duplicates, as shown here in red. Omitting these repeated lines produces a short. So there's the pulse table with the 5 duplicate lines removed. Moving on to the low pass case, this produces a quite different table. In the high pass case, only X is pulse, but in the low pass case, both X and Y are pulse. Essentially, this is Oroning, aligning Y with X in the one case and aligning Y with Z in the other. So G's P-level behavior in the low pass case is as shown in this table. And that's a table we've seen before. It's the pulse table Slutz started with when he did his switcheroo to produce the 2 different Boolean functions. But by pulse reparsing, we've produced 2 different pulse tables. There's no need to do the switching of zeros and ones to get the 2 different Boolean functions. If P signifies 1 and N signifies 0, the first table becomes and the second is or, inclusive disjunction. So that's my analysis of Oroning. Oroning happens at the P level. Oroning is pulse reparsing. Now to that same or different question. Pulse parsing or reparsing is selecting or reselecting which portions of the waveform are pulses. Oroning is effectively pulse reparsing. On one parse, you produce pulse, no pulse, no pulse. On the other parse, you produce pulse, no pulse, pulse. On one parsing, the third wave crest is not a pulse, and on the other parsing, it is a pulse. Slutzing, too, can be seen as pulse reparsing. You start off with a train of pulses and no pulses, and then you reparse, and you get a different pulse train. It's a rather extreme form of pulse reparsing, but it's pulse reparsing nevertheless. You parse the lows as pulses and the highs as no pulses. Pulse reparsing takes the place of switching labels at the B level. I call this deep slutzing to distinguish it from the original form of slutzing, the mere label swapping. Although the original form of slutzing can be perfectly simulated by deep slutzing. Upshot, there's no essential difference between slutzing and Oroning. Both are manifestations of the more fundamental underlying phenomenon of pulse reparsing. Next, I want to take a look back at that text I circled in Bloch's slide. Bloch says, "It is an intrinsic fact that a gate is an AND or OR but not a XOR gate. A Slutz-type gate," he says, "can be described as an OR gate and an AND gate, but not as a XOR gate." But that's not so. Here's a rather simple theorem. There exists a gate, call it B, with the following properties. Firstly, B's p-level description in the low parse case is PPP, PNP, NPP, NNN. So here I'm just squashing down the table describing B's p-level behavior into a single line. It's really a table, but I've horizontalized it. And so, given that that's B's p-level description, B can slutz between inclusive disjunction and AND. Secondly, B's p-level description in the high parse case is PPN, PNP, NPP, NNN. And so in this case, B slutzes between exclusive disjunction and if and only if. That's to say, B can be described as an inclusive OR gate and as an AND gate and as an exclusive OR gate. I suppose Bloch thought his claim was true because while he knew about slutzing, he'd rediscovered slutzing, he didn't consider pulse reparsing. And so things are more complicated than he imagined. Section 7. So far we've been doing the pulse parsing and pulse reparsing in our minds, kind of purely conceptually, by drawing lines on a piece of paper or on the screen. How can pulse reparsing and pulse parsing be done by mechanisms? Engineers have devices called transition detectors that can be used to parse and reparse a waveform. This is just an example that I grabbed from the IEEE electron device letters. At the top left, a regular rectangular wave is going in as input, and the output comes out at the top right. That green pulse train at the top right. Here's a closer look at the output. And the pulses are labeled at the B level. And the point about the output is that the pulses, and hence the bits, form a random sequence. Random pulses are naturally a useful commodity for all sorts of purposes in the modern world: cryptography, user identification, online learning algorithms, and many other applications. And this device is a promising new way of creating random pulse trains. The pulse parsing, as I call it, is done making use of this part of the device. The parsing threshold varies stochastically, in this case because of a nano-level property of the material they used, vanadium dioxide, and this results in a stochastic parsing of the input waveform. What goes in is a perfectly regular series of wave crests, and what is produced is a random series of pulses and no pulses. But this is just one example of how you can carry out pulse parsing by means of real electronics. Having quickly looked at this one example, in what follows I'm going to abstract away from all hardware details about how the pulse parsing is to be implemented. I'm going to describe the concept of probing a gate. Any gate will do to illustrate probing, say gate B from my previous theorem. Abstracting away from details of circuitry, what I'll call a probe parses the output of the gate. The probe taps off one of the available functions. The output of the probe is a train of pulses and no pulses. Now that deep slutzing is on stage, we can abandon the idea of switching the bit labels on the pulses and no pulses and stick instead with a single convention, say 1 for pulse and 0 for no pulse. Under that convention, the green probe taps the AND function off the gate. A different probe can tap off another of the available functions, inclusive or both probes may operate concurrently. This is the concept of multi-availability. Two different functions are tapped off the one gate. Another probe might concurrently tap off exclusive disjunction. Gate B indeterminately computes at least 3 different functions. Armed with the right probe, you can tap off whichever of the functions you need, or by using multiple probes, you can tap off several different functions from the gate. Section 8. Objections to the very idea of computational indeterminacy. First objection. At the P level, there is no indeterminacy, and the P level is the principal computational level. Indeterminacy arises only from swapping around the labels at the B level, and that's a rather shallow effect. There is no indeterminacy of computation at the computational level that really matters, the P level. But that's simply not correct. Pulse reparsing introduces indeterminacy at the P level. Indeterminacy is not just a B level phenomenon. Indeterminacy at the P level, achieved by pulse reparsing, either Oronian pulse reparsing or Slutzian pulse reparsing, is where all the interest lies. So this objection just gets things completely wrong. On to the next objection. Second objection. Indeterminacy is observer relative. There is no intrinsic computational indeterminacy. What the computer itself does is completely determinate, but we, the observers, can take up different perspectives on what it does, and this introduces what you can call indeterminacy if you like. But this indeterminacy is in the eye of the beholder of the computation, not in the computation itself. Intrinsically, computation is determinate. Not so. Returning to the example of the triple probed gate, it simply is not an observer relative fact that the 3 probes are tapping off different pulse trains from gate B. It is a fact that they are, but that's not an observer-relative fact. As I mentioned before, John Searle is heavily invested in the distinction between the observer-relative and the intrinsic, and he has a criterion, Searle's criterion, for a feature f of item O being intrinsic as opposed to being observer-relative. His criterion is, if we all died, O would still have f. That's from his book, The Rediscovery of Mind. Searle's own example is f equals a nice time for a picnic. By his criterion, nice time for a picnic is quite rightly an observer-relative feature. By Searle's criterion, though, multi-availability is an intrinsic feature. If we all died, the 3 probes would continue tapping off different pulse trains. It's an intrinsic feature of, for example, gate B, that it's indeterminate what B computes. B intrinsically makes a number of different functions available. On now to a third objection, and it's the last I'm going to mention here. Objection 3. In the end, a gate is just a physical mechanism, a determinate physical mechanism. At the W level, the physical level, there is no indeterminacy. The dynamics at the W level are determinately what they are. It is only when theorists show up with their labels, P, N, 1, 0, and so forth, that there appears to be indeterminacy. But if there are gates in the reptilian brain, say, then we can safely assume that these would have functioned in the same way before and after human theorists arrived with their labels. At the W level, the dynamics simply roll merrily on in the same determinate way, irrespective of whether anyone has labelled the waveforms or not. Indeterminacy is a pseudo-problem, a distracting artifact of human theorizing. Response. Let's consider again the triple-probed gate. If a device like this exists in the reptilian brain, then it's an intrinsic fact that pulse reparsing occurs in the reptilian brain. What the illustration depicts may indeed have been occurring inside reptile skulls for millennia before human beings arrived on the scene. Labels like P and 1 are very useful for describing pulse reparsing, multi-availability and indeterminacy, but the labels don't create the indeterminacy. So much for objections. Hopefully these were instructive objections. It's time to move on from objections to applications. Section 9, exploiting indeterminacy. In this picture, the trough represents a multiply specifiable device, and the pigs represent mechanisms that access this device. This is the trough model for utilising indeterminacy. Device D is indeterminately computing a number of different functions, F1, F2, and so on. D is situated in a milieu of uptake mechanisms corresponding to the pigs. Each uptake mechanism taps off a single one of the functions indeterminately computed by D. For example, D might be a simple Boolean gate of the sorts that we've looked at, indeterminately computing just a small number of functions. Or D might be a much more complex hardware unit. Or D might be a neural structure in the brain. So that's the trough model. Lastly, some suggestions about the possible significance of indeterminacy. Firstly, there are potential applications in hardware design. Slutz, of course, described the first. Secondly, Does the evolving brain perhaps make use of indeterminacy in order to repurpose existing neural structures for new cognitive tasks? This is the massive multiple specifiability hypothesis, which is discussed in much more detail in the article with Neer and Marty that I mentioned earlier. So the hypothesis is that a multiply specifiable neural structure may be used to serve a range of different purposes, including cognitive and regulatory functions, by exploiting the different computations performed by the structure, and this may occur extensively throughout the brain. And thirdly, the strategy of achieving plasticity of function via indeterminacy may also prove useful in engineering artificial cognitive systems. That's it. Thanks for listening.
Thank you very much, Jack. It was really very interesting, fascinating, and what is important, you presented it the way that it can be understood relatively easy. It doesn't mean that it was completely simple, but I could see that you managed to explain quite sophisticated aspects of indeterminacy in a way that general audience could understand it. Thank you very much. I regret, but we have this schedule and we won't be able to give audience a chance to ask questions. So maybe there will be some possibility to do something about this. But at this point, I will just say that thank you very much.